Um, so yes, thank you very much. Yeah, I'm Alex Blair. I'm from the UK Atomic Energy Authority and going to be presenting a little today about our work in adding MFEM as a possible backend, as an optional backend for use with the Moose framework. If you haven't heard of Moose, you will hear about it today as well. Um, I just want to say before we start, this is due to a whole bunch of people at UKAEA and also at STFC, Science and Technology Facilities Council in the UK. And we had immense support as well from Idaho National Lab, who maintain Moose, and the core development team over there, who have been extremely supportive in helping us and helping get this into the main Moose repo. So, without further ado, I'm going to kick off by telling everyone what Moose is. Introduction, if you haven't heard of it before, what the Moose framework is, and why we are interested in it at UK Atomic Energy Authority. What we can do with the MFEM finite element backend in Moose, which has been recently added in April as an option for people to use. Talk about more recent additions that have come in since then, before telling everyone about the road ahead and what the future looks like before wrapping up. So, without further ado, what is Moose, and what are we talking about here? So Moose is a large-scale open-source parallel finite element framework from Idaho National Lab that's built originally on the libmesh finite element library. It's got a very large and active user community. I think at the moment it's standing about 2,037 stars on GitHub, so just pretty much neck and neck with MFEM, but ever so slightly at the moment. It's been shown to be, there are examples for scaling typical problems for H1 problems in particular, tens of thousands of CPU cores. Now, why do we care about it at UKAEA? Well, there's a real need for having scalable tools suitable for use for end engineers and the end user, capable of modeling systems containing a diverse range of couplable multiphysics. This could be, we need to verify components for use in fusion reactors in silico in order to meet kind of the ambitious time goals for next generation fusion reactors. And we need to be able to simulate components and materials in those scenarios in order to help de-risk those components. And so we really need to have a tool that an engineer who's actually doing the qualification of these components and stuff is able to use without having to kind of recompile and go to great lengths to add bits of physics or take bits of physics away. We need to have a tool that they can use, has a simple interface that they're able to interact with, that contains the physics they need, and that they're able to add new bits of physics into, or with the support of developers like ourselves, to cover their relevant use cases for their problems, which in kind of fusion components is often very challenging, mixed multiphysics problems, highly nonlinear in many cases that are really stretching what we can do. We want to get them away from using the typical commercial tools that commonly dominate the conventional engineering workflow here, and onto using the kind of scalable tools that we in this community have been able to use. So why Moose in particular? Well, it has a nice simple user interface. I mean, most input files from Moose are simple kind of hierarchical input text format files where the user can actually add modules in a text block. You'll see a bit later on what that looks like to define their problem. It's got a very modular design with quite a wide existing ecosystem of existing Moose applications that some of them couple with common external tools like NECRS for thermodynamic simulation or OpenMC for modeling kind of neutronics behavior and things, alongside Moose apps which are dedicated to solving dedicated piece of physics for in other domains. So very healthy and wide ecosystem. Some of those are open source, some of those are closed source, but the core framework here is open source. And following robust sort of software quality assurance procedures, they're following the Integrate 1 standard, which is useful looking ahead for when we will want to make sure we can convince regulators of suitability of components for use in future reactors. It's important that we can show that the tools we're using to qualify them are suitably appropriate. And has very useful for helping bring our engineering, bring the end users across to away from their existing commercial tools and onto scalable tools. It has a wide range of existing multiphysics modules available out of the box that really helps in able to get them up and running and playing with things without having to convince them to wait for new features to be added straight away. So here are a selection from the Moose website of ones that are available in the base Moose framework. Some of these are used more than others, and some of these are more developed than others. So obviously things like solid mechanics, heat transfer, things like that are very much workhorses in this space. And we've had real success in being able to get our the kind of early adopters up and running with on be able to translate their engineering problems over to use Moose and deploy their problems on HPC systems. But the underlying FE library has a few limitations. So libmesh, I think one key issues is it doesn't have any GPU support, largely limited to low order FEs in the bulk case, and relatively limited support for kind of HKL and HDiv conforming vector finite element types that we need for many of the formulations we want to use, particularly for electromagnetism. And given we're primarily looking at confinement fusion at UKAEA, that is a real issue when we want to look at behavior in field. So you probably have realized by now that particularly that no GPU support is something that whilst libmesh suffers from, MFEM it has shown over the last several talks over the last couple of days the capabilities there, and with this extra support around the other finite element types that we can avail on MFEM as well, motivated the option of can we get MFEM available as a backend for Moose as an alternative for people to use where libmesh isn't suitable for these kind of problems. And that's what we did. We this time last year in the at the MFEM Community Workshop 2024, we reported on a Moose application that sat on top of Moose that allowed problem setup and assembly of MFEM FE problems that was integrated with sat on top of Moose and interacted with Moose as a Moose application. Since then, in April, that was fully migrated upstream and merged into the main Moose repository. I have to say at this point, that was thanks to a lot of back and forth and a lot of work from Alex Lindsay and Loden Harbour from the INL team on this. So I want to give thanks to them for all their support with that, and subsequently with advice back and forth and conversations and later PRs on this front. They really have been an immense help. They continue to be. At the moment, if you immediately, if you decide to check out the Moose framework and the MFEM capabilities currently available in it, we currently support things like setting up and solving currently linear problems on GPU or CPU using the range of operator assembly levels that MFEM supports. We support MFEM's range of FE types, arbitrary order, across the RAM complex. So you're able to use your NAND elements or Ravi-Smar elements as well as your typical H1 and L2 conforming ones. We support a range of the preconditioner and solver options, so including like hyper, SuperLU, that exposed from MFEM's interface with those. We support transient and steady state problems. Currently, transient problems are limited to those with backward Euler, effectively, so implicit problems there, but we're working on extending that. We support mixed FE problem setup as well. So we've got some examples, like the Darcy problem from example 5 that people want to play around with as well are available. And recently we've added support for interaction with Moose's multi-app functionality, which I'll talk about a bit as a way of orchestrating solves between related FE problems and transferring data back and forth between them. If you're interested in getting started, have a look at the slides after and follow this link. You'll be able to find a whole bunch of information on how to install, how to set up your problem, and so forth. So if anyone interested, highly recommend following those links. Effectively, all that's needed is to go to the Getting Started page on the Moose website, run a handful of scripts to build the the dependencies for the extra dependencies for conduit and things as required, and then just configure with -- with MFEM rather than just configuring and default for Moose, and then building as you would regularly any other Moose problem. And there's a whole bunch of extra information on how to install. If you run into any problems, you should be able to find your solution here. But they're very straightforward and effectively running a script to pull and build MFEM, and then configuring Moose with MFEM support. And then you have the ability to use it. What does it look like for the user? I mentioned this is that effectively the user interacts with effectively a text file, a hierarchical input text file, where they input the ingredients to their problem. So this is a simple diffusion problem. This is a full input file on the screen. This is what your end user would interact with. Declaring that they want to run with the MFEM backend rather than default libmesh one is done by this kind of problem block at the top. With a simple MFEM problem type. They can declare their mesh, supports all the effectively that gets piped to the regular MFEM mesh constructor, so all the mesh types that MFEM supports are supported there as well. And then the user sets up their finite element spaces and any variables that depend on them. And it could be multiple, obviously. Then they can add the boundary conditions and integrators that they want to add to their system. In Moose, those are kernels, which can cause some confusion. We overload that word, but these boundary conditions kernels, we have a couple of Dirichlet BCs here that apply essential BCs on those boundaries. They could be integrated BCs, and our kernels effectively add integrators to equation system backend that effectively accumulates and builds our block operator that we want to be using to solve the problem behind the scenes. So these objects are really returning one or more integrators that get added to the block system as needed. We support mixed mixed bilinear form integration and things in this as well. So for systems with mixed systems. I should note at this point as well, since last time I showed this kind of example, users are now able to refer to blocks and boundaries, subdomains and boundaries in their system by name, not just by attribute ID, thanks to all the attribute set work that went in last year, which makes it a lot more readable for the end engineer to work out where on earth they're applying a material or a boundary condition to in their problem. And then finally, for setting up the actual the solver and the methods how they're assembling their problem, the user effectively creates a preconditioner and can attach that to a solver as required. Like I say, we can also support direct solvers here. And the executioner block then controls what device and what assembly level they would like to run at. We've got a default example here with running on CPU with legacy assembly, but you could run with CUDA with a partial assembly by changing these flags. We also support MFEM's seed backend, so putting seed, CUDA, and things like that is also supported here as well, and running with like assembly level equals none. And finally, spitting out results. That you could also add some post-processors there if you wish, but we support the range of data collections from Moose. Since last time, we've also added support for the conduit data collection in addition to things like regular parity data collections and like. For getting a feel for a problem which might be more in your own domain, we've got a number of default example files up at the link at the top here. We've got examples showing off what those input files look like for running kind of transient thermal peak conduction kind of style problems. EM problems, here is just a mini to static field around a current carrying coil, and simple linear SST problems, as we've seen a few times over the last couple of days. These will also go through some of the math and the kind of background on how you could, and hopefully inspire you if you have any specific requirements to help inform how you would possibly set up your own problem within this framework. We've also tested bigger problems as well, and we hope to continue doing this. So this was a problem we ran for looking at the the gravitational loads on the vacuum vessel of the Mast U tokamak at UKAEA, which was thanks to a mesh that was toiled over by someone else in the larger group, Bill Ellis, where we effectively looked at especially a linear elasticity problem subject to a gravitational load on the system, and looking at the relative deformations. On the left is the native MOOS result for running on CPU, for I think that one was on 4 million elements or so. And on the right is the equivalent with the MFEM backend. We see consistent results, and also we've run that up to I think 127 million elements at the moment, including on GPU across multiple GPUs, all finding that we find effectively minimal overhead compared to running with native MFEM directly. We're fairly convinced that we don't see any significant performance here by running using MOOS to orchestrate the setup and solve the problem. And yeah, it's currently supported for single state problems, but we are playing around with this. I think we're currently working on extending this to include the field around coil sets for this kind of representative example. So. More recently, there's been extensive activity in extending this, some of the newer features that have happened in the last few months. One of the most important, probably, for helping people play and couple solves together is support for MFEM problems within the multi-app framework. So MOOS has quite a nice set of features for orchestrating the execution of sub-applications. So effectively, you can have multiple input files that can be solving sub-parts of your problem. It might be used to solve some kind of source field or source file for in a sub-app, and you pass it up to a parent app to do something with that. Some of these can be transient, steady state, mix and match as required. And so it's particularly useful when you want to be solving problems that span different different time or length scales, and you want to be able to have some coupling between those two systems in a relatively loose sense. It's supported for systems where at the moment the two meshes in the sub app and the parent app are the same, although we are looking to add GSLib integration here to be able to do some interpolation between different meshes. And this has been very useful in the nice thing about this, and more generally with the multi-app way of developing things is it makes it very it helps split up the development burden here for solving problems at different length and time scales. So someone could be working on a problem at some smaller length scale or a longer time scale, and fairly easily interact and share that transfer that data back and forth with that app running at a different length and time scale just by changing your input file for your relevant case here. So and when you want to execute that, how often you want to execute, and a transient problem can all be controlled as well. Another thing we've spent time on is improving how easy it is for end users to specify coefficients, whether they be material properties or coefficients coming from variables or et cetera, et cetera. Effectively, whenever someone's setting up a MOOS object that requires a coefficient, there are now a whole number of ways that a user can specify that coefficient. They can either effectively pass it in directly by value in that input file. If it's a simple constant, they can pass in the name of a variable, Hawk's variable, which will effectively link it to a grid function or a vector grid function coefficient as appropriate. They can link in a name of a function that allows someone to possibly have a function space and time that is provided in their input file that can be used to set up used for that coefficient for a boundary condition or otherwise. And finally, you can also, for material properties that are typically piecewise across blocks, they can create it through a kind of a functor material, and then to enforce the piecewise nature of that property across different across subdomains of the problem with different material parameters. This again has made it quite significantly has sped up how easy it is for people to mix and match and try different material models out here, but also has very much reduced the number of kind of objects we've needed to maintain, because we've got one kernel, one method of adding an integrator for all these sources, which has reduced the overall footprint as well. And we've also added support for submeshes. So for those who want to be using a domain submesh or a boundary submesh in their problem, that can effectively be added in a suitable block in their input file, declaring the including the set of subdomain names or attributes that that constitute the submesh they want to create, and which they can then use in setting up their finite element spaces and any downstream variables thereof. We've used this, for instance, for this example is like a closed coil where we impose a particular loop voltage by extracting a submesh on a 1 element thick transition layer on one side of a cut, which we then can use to generate the divergence-free current representation of the divergence-free current density around the loop, and we can also couple that to a magnetostatic or magnetodynamic solve to include the field distribution around it in the vacuum region. So extremely useful, particularly useful for improving conditioning for a range of formulations that similar to this can be used this way. And we do support, like I say, boundary submeshes this way too. We're looking to for a number of uses for that as well, which we'll see later on. And for high order problems, we recently added support for low order refined solvers. And to make sure that we can actually still get suitable formats up for when using high order FE types appropriately. Yes, effectively bypassing in an extra flag when setting up the preconditioner as required. What are we doing next? So there's a handful of issues currently up in PRs that are currently under review, and we expect to be relatively soon reviewed and commented on. Adaptive mesh refinement is kind of the first of those. We've got something up and working in branch at the moment, and we expect to effectively merge it with the Moose-like syntax of declaring allowing the users to specify that they want to include adaptivity in their problem. We've also have initial support and under review for adding support for complex systems, so support for complex grid function, complex linear form, sysqual linear form, etc. We've got like this example bottom left here is effectively a waveguide with obstruction in the center of it. It has some absorption properties to it, which we are also effectively this first foray into be able to extend this to support problems in the frequency domain as well. And as I mentioned earlier, integration with GSLib is inbound, so we can do that kind of mesh-to-mesh interpolation, but we can also use it for post-processes that are intended to sample along a subset of points / lines in the mesh that the user can specify. And we're also looking at, more generally, we're working on allowing transfers in the multi-app framework between libmesh and MFEM representations. It's particularly important to allow us to have multi-app simulations that can couple with tools that are very much currently working with libmesh side of Moose at the moment. So this is very much for interoperability and allow users to potentially add bits of physics that are intended to be set up and solved with MFEM without necessarily doing it in one enormous step. And finally, very much looking at adding initial examples for contact in these problems, as that remains a significant request and from our users to be able to enforce contact in their relevant problems. But probably more than anything else, we are very much working on adding support for nonlinear systems. So everything I've said so far is all linear systems, and because we can allow the user to add variables kind of from that input file, they can add many variables they want in that system. We're very interested in the work we saw, we've we've been following a lot of the work with DFEM, particularly in the definition of its parametric nonlinear operator, because it aligns quite nicely with how regular integrators are added in libmesh-based MOOS. So we're very much following that and looking to scoping how best to integrate that into what we have in MOOS at the moment. Whilst that obviously, as DFEM is being developed, we're also investigating just adding support for coefficients that can be nonlinear functions of other coefficients and grid functions in order to get something that's functional for users in the near term, although that won't obviously be performant, particularly on GPU. We know that won't be anywhere near as good as just be able to do this with DFEM. So very interested in what happens next with DFEM, and very much looking to integrate that into our approach for nonlinear systems going forward. So to wrap up, MFEM is now available. If you want to set up a problem with MFEM in MOOS, go onto the MOOS website, read the documentation, and let me know if there are any issues, but hopefully pull the examples and have a play. We've had support for a whole load of example finite problems on CPU and GPU. We're adding GPU support within MOOS for the first time this way. And we've got example input files for your thermal, mechanical, EM problems. We've got some Darcy flow problems in there as well. And we're actively working in improving interoperability with the existing libmesh side of MOOS, so help reduce the barrier to the entry for people trying out using the MFEM backend within the MOOS framework. And strap up, nonlinear systems are the next step. Contributions will be welcome, so thank you.
Thank you. Any questions?
Yeah, nice talk. You mentioned that you could specify custom function coefficients in the input file, and I was just wondering, how do you parse functions from the
at the moment we have we're leveraging effectively a function parser that exists in the libmesh side of MOOS, and that is part of the reason we're having to spend some time in adding support for functions of other variables. Yeah, it's effectively there's an inbuilt parser for which I think depends on I can't remember if it's I don't want to say speak out of turn which library actually uses under the hood to do that parsing, but it's effectively just a spatial temporal function. So it will detect whether you've got like X, Y, or Z and T in your function expression, along with elementary functions like sine, cos, export, whatever. Sure. So if you want to add a simple function of spatial time, it's a way for the user to impose that without having to rebuild everything.
Thank you.
I'm curious, this multi-app, is that MFEM effort or is that MOOS effort?
That's MOOS. So MOOS, the full information on this can be found at this link. But yeah, this is how MOOS orchestrates kind of libmesh problems internally anyway. And yeah, like I say, it's extremely useful when wanting to compose, potentially add coupling into problems that didn't originally have a coupling and build up a lot of coupling in your problem system. Add physics to it. Extremely useful for that. And so yeah, there's a whole range of existing examples that do this for the libmesh side of MOOS. But yeah, we've added support now, so people can do it from MFEM to MFEM on the same problem mesh. They can leverage that orchestration.
I saw something similar on MFEM branch. Is on the active development for multi-app. Is it?
Yeah, it is.
Okay.
We're building that capability for the MFEM side as well to bring in external apps and support existing or new apps. I didn't know people knew about it, but
Put it
in a branch.
Yeah. Someone sent to me, so that's why I know. Yeah.
Sure. So the people apparently had to do a good job.
So in this multi-app case, what happens when one of the app is on the GPU and the other is on the CPU?
At the moment, they've got to be on the same device. So at the moment, if you've got the parent app is using a CPU, then the downstream sub app must be on CPU. And if your parent app is on device, then so is the downstream one.
Yeah, the reason I'm asking is that the GPU kernels are one thing, but there's also the memory manager,
Yeah.
and something like this need to be keenly aware of the different memory spaces and minimize the transfer.
Yeah.